Hello students, this is Mrs. Jennifer Cruz from Lilavati Lalji Dayal High School and College of Commerce. And in today's Science Fun class, students, we shall study chapter number 4, that is effects of electric current. So before starting with this interesting chapter, students, let me tell you all that the total weightage of this chapter is 7 marks with option and 5 marks without option. So let's begin with this interesting chapter. So students, in this chapter, we shall cover up the following topics. First, energy transfer in electric circuit. Second, heating effects of electric current. And third, the magnetic effects of electric current. So let's begin. So students, let us first understand energy transfer in electric circuits. Okay. So in the earlier standard, students, you've already learned about static electricity, right? We studied about the object becoming positively and negatively charged, and also the transfer of negatively charged particles from one object to another object, and also the electric current. That is, an electric current is a stream of charged particles such as electrons or ions. Okay. So moving through an electric conductor. Okay. So what is electric power, students? So electric power is nothing but the energy per unit time converted by an electric circuit into another form of energy. Okay. So here in students, we already know that the power through a circuit is equal to the voltage multiplied by the current in a circuit. That is, P is equal to VI. So it is possible to determine the power dissipated in a single resistor if we combine this expression with the Ohm's law. That is, V is equal to IR. Okay. So students, we already know that the SI unit of electric power is 1 volt, okay, which is very small unit. So students, this becomes very useful in circuits with more than one resistor to determine the power dissipated in each one. So combining these two equations, we can get an expression of electric power that involves only the current and resistance in a circuit. So let's move on to the next slide. That is the heating effects of electric current. Okay. So here in students, when a current flows through a conductor, heat energy generates in the conductor. Okay. So the heating effect that is there. Okay. The working of it is seen in the working of the electric bulb, electric iron, okay, fuse wire. So all these things are based on the heating effect of the electric current. So the heating effect of the electric current, students, it depends on 3 factors. First, the resistance of the conductor. That is, the higher resistance will always produce more heat. Second, the time for which the current flows. So longer the time, the amount of heat production is higher. So higher the time, higher is the heat production. Third, higher the current, the amount of heat generation is also larger. So students, hence the heating effect produced by an electric current I through a conductor of resistance R for a time t is given by H is equal to I to RT. This equation is also termed as the Joule's equation of electrical heating. Okay. So let's move on to the next slide, students. And that is the right hand thumb rule. Okay. So what is a right hand thumb rule, students? So it is a very convenient rule for finding out the direction of the magnetic field produced by a current flowing through an electric conductor. So as you can see in the diagram, okay, what is done, that the conductor is held in the right hand in such a way that the thumb points in the direction of the current. Okay, as you can see in the diagram, the thumb is in the position towards the electric current, and the fingers, okay, then turn your fingers around the current The direction of your fingers is the direction of the magnetic lines of force. So the direction of the thumb tells you about the electric current, and the direction of your fingers that are there tells you about the direction of the magnetic lines of force. Okay. Now, moving on towards the next topic, students, that is the electric motor. So what is an electric motor, students? Basically, it is a device which converts electric energy into mechanical energy. So this device which conducts, which converts electric energy into mechanical energy can be said as an electric motor. So it works on the principle that a current carrying conductor placed in a magnetic field, okay, it always experiences a force. So basically, students, let's see what is the working of electric motor about and what is electric motor all about. So the electric motor, students, it consists of a rectangular loop of copper wire having resistive coating, as you can see in the diagram of the electric motor. It is placed between the two, okay, the north pole and the south pole of a magnet in such a way that its branches, okay, here you can see its branches AB, okay, AB and CD are perpendicular to the direction of magnetic field. The two ends of the loop are connected into two halves, okay, that is X and Y. So you can see it is divided into X and Y, okay, and the two halves of the ring have a resistive coating, okay, on their inner surface, which are tightly fitted on the axle. Now the two halves of the spring, okay, that is the split ring that is there, X and Y, have their outer conducting surfaces in contact with two stationary carbon brushes, E and F respectively, okay. So here we have the two carbon brushes, E and F respectively. So students, when the circuit is completed as shown in the figure, okay, which we already saw, the current flows in the branch AB of the loop from A to B through the carbon brushes E and F. So since the direction of the magnetic field is from North Pole to South Pole, according to the Flemings left-hand rule, a force is exerted on the branch AB and it pushes it down. The current in the CD branch is in an opposite direction, okay, to that in the AB branch, and therefore a force is exerted on the branch CD in upward direction. Thus, students, the loop and the axle starts rotating in an anti-clockwise direction. Okay. So basically, after the half rotation, the two halves of the split ring, okay, X and Y, comes in contact with carbon brushes F and E respectively. And the current in a loop starts flowing in the direction DCBA. Therefore, a force is exerted on the branch DC in downward direction and on the branch BA in the upward direction, and the loop continues to rotate in the anti-clockwise direction. Thus, students, the current in the loop is reversed after each half rotation, and the loop and the axle continue to rotate in the anti-clockwise direction. So commercial motors run on the same principle, but practical changes are made in their construction. So students, an electric motor is also used in a mixer, okay, refrigerator, washing machine, an electric fan, tape recorder, computers, or pump. So this was all about electric motor. Let's move on to the next slide. That is Fleming's right hand rule. Okay. So students, as you can see, if a conductor is forcefully brought under a magnetic field, there will be an induced current in that conductor. And the direction of this force can be found using Fleming's right hand rule. Okay. So herein, if you can see in the diagram, what can we see? the thumb is stretched. Okay, we have to stretch the thumb, the index finger, and the middle finger of the right hand in such a way that they are perpendicular to each other. So in this position, students, the thumb indicates the direction of the motion of the conductor. Okay, the index finger denotes the direction of the magnetic field, and the middle finger shows the direction of the induced current. So this is all about Fleming's right hand rule. Moving on to the next topic, that is magnetic effects of electric current of Fleming's left hand rule. Okay, so what is Fleming's left hand rule saying? A current carrying conductor comes under a magnetic field, there will be a force acting on the conductor, and the direction of this force can be found using Fleming's left hand rule. Okay, it's also known as Fleming's left hand rule for motors. Okay, so in the diagram you can see, student, the left hand thumb, okay, the index finger and the middle finger are stretched so as to be perpendicular to each other. So if the index finger is in the direction of the magnetic field, then the middle finger points the direction of the current, and the direction of the thumb is in the direction of the force of the conductor. Okay, so students, with this we've completed this chapter. Thank you.